Here are some examples, conservation of momentum word problems. A ball of mass 3 kilograms moving at 2 meters per second eastward strikes head-on a ball of mass 1 kilogram that is moving at 2 meters per second westward. So I've drawn pictures of the 3 kilogram ball moving to the east is to the right, and the 1 kilogram ball moving to the west. And I had to make that a negative 2 meters per second because it's going in the opposite direction. The balls stick together after the impact. So essentially now they have a combined mass of 4 kilograms. What is the magnitude and direction of the velocity of the combined mass after the collision? So we want this final velocity. So what we know is that momentum before the collision is equal to momentum after the collision. So the momentum before the collision would be 3 kilograms times 2 meters per second plus 1 kilogram times negative 2 meters per second. So that would be 6 plus negative 2 or 4 kilogram meters per second on the left. On the right, we have 4 kilograms times the velocity, and maybe we can see right here that then the velocity is going to have to be 1 meter per second because 4 times 1 is 4. And since it's a positive number, it's going to be east. Okay, oops, what happened there? All right, number 2. One way of measuring the muzzle velocity of a bullet is to fire it horizontally into a massive block of wood placed on a cart. Now, I have a little example here that isn't exactly the same, but I do think it's worth looking at. The ballistic pendulum is a method for computing the speed of a bullet as it leaves a firearm. So if I hit fire, you can see it hits the pendulum and swings up, and based on how high it goes, we could determine the initial velocity of the bullet. That's a little different than this scenario. In this scenario, it's going to be fired into a massive block of wood on a cart. So this is going to be an inelastic collision. So here's the bullet. Here's the block of wood. And I'm looking at what happens before the collision and then after the collision. The bullet will be embedded in the block of wood. Now it's like one piece. Okay, assuming no friction, we then measure the velocity with which the wood containing the bullet and the cart begin to move. In one experiment, the bullet had a mass of 50 grams. So I'm changing that to kilograms. I divide by 1,000. And the wood in the cart had a mass of 20 kilograms. After the shot, so let me do this. So the sum is 20.050 kilograms. After the shot, the cart, the wood, the bullet moved at a constant speed, traveling 8 meters in 0.4 seconds. So the velocity is going to be 8 meters in 0.4 seconds. So I can divide to determine the speed. So I'm getting out my trusty calculator here. And I get a velocity of 20 meters per second. From this data, determine the original speed of the bullet. Okay, so the bullet was moving initially. The wood was not. So this is an inelastic collision. So the mass of the bullet times the velocity of the bullet initially plus the mass of the wood times the velocity of the wood initially should equal the mass of the bullet plus the mass of the wood times the final velocity. So 0.050 times the velocity of the bullet plus 0, this is 20 times 0, so that's 0, equals 20.050 times, that's 20 meters per second. So now I solve this. So I'm going to take 20.050 times 20. And then I'm going to divide by 0.05. And I get that the initial velocity of the bullet was 8,020 meters per second. That's quite fast, even for a bullet. All right, let's try number 3. A raft of mass 180 kilograms carries 2 swimmers of mass 50 kilograms and 80 kilograms. The raft is initially floating at rest. The 2 swimmers simultaneously dive off opposite ends of the raft, each with a horizontal velocity of 3 meters per second. With what velocity and in what direction does the raft start to move? And then the next question is, what is the velocity of the center of mass of the system that includes the swimmers in the raft? Is this an open or closed system? Okay, so let's look at this conservation stuff again. And here I have a person on a floating raft, and I'm going to have them walk on the raft. Look at what happens. The center of mass of the system stays in the same place as they walk because there's no external force on this. I wish I could put a second person on here. In the scenario that we're looking at, we actually would have 2 people on the raft, and they're jumping off in opposite directions. So let me try to sketch this. So here's the raft. Let's put a 50 kilogram swimmer who's going to jump off one end. And let's put an 80 kilogram swimmer who's going to jump off the other end. The velocity of each is 3 meters per second. Now the 50 kilogram swimmer is going to jump off in the opposite direction, so I'm going to call that negative 3 meters per second. Okay, and then the raft has a mass of 180 kilograms. And its initial velocity is 0. Actually, the initial velocity of all of them is 0 because the swimmers initially are at rest. So this 3 meters per second is what happens after the collision. So if I were really being careful, I'd actually draw this twice. And in the second picture, they'd be diving off with their velocities. And we'd be wanting to know what the velocity of the raft is. So the initial momentum of the system is 0 because initially none of the people or the raft are moving. The final momentum of the system is equal to the 50 kilogram person, their mass, times their velocity, which is negative 3 meters per second, plus the mass of the raft, that's 180, times the velocity of the raft, which we don't know, plus the 80 kilogram person times the 3 meters per second. So we have 0 equals negative 150, again, this is kilogram meters per second, plus 180V plus 240. 0 equals, let's see, what is this? 90 plus 180V. I'd subtract 90 from both sides and divide by 180, so I get V is negative 0.5 meters per second. So that tells me that the raft is going to go to the left at 0.5 meters per second, or you could say negative 0.5 meters per second. You shouldn't say both, though. Either say negative 0.5 meters per second or left at 0.5 meters per second. If you say both, it's like a double negative, like I ain't never. And we don't want to do that. Okay, let's try one more example. A ball with mass m and velocity v has a perfectly elastic collision with a ball of mass lowercase m. Find the velocity of the second ball. Then find the velocity of both balls if they have a perfectly inelastic collision. So perfectly elastic means all momentum is transferred. So the first ball has a momentum of capital M times capital V. So we'll call that ball number 1. So ball number 2 has the same momentum. And so what we would like to know is, what is this V2? So to solve for V2, I would say it's capital MV over lowercase m. Or you could write it as capital M over lowercase m times V. Okay, let's look at what happens if we have an inelastic collision. An inelastic collision, they stick together. We're going to assume that ball 2 has an initial velocity of 0. So initially, before the collision, we've got ball number 1 with mass m and velocity v, and ball number 2 with mass lowercase m and velocity 0. So this actually has no momentum of its own. And then after the collision, they stick together. I'll just call it VF, their final velocity, is what I want to find. So the momentum of both of them stuck together after the collision is equal to big M plus little m times VF. And, oops, this momentum after the collision must equal this momentum before the collision. And I'll solve it for VF. Oops. And there we have it. So we're really just practicing solving with variables instead of numbers. All right, thanks for watching my video, and I'll see you in class.